How's it going, everybody? Welcome to my CppCon 2020 talk entitled Structure and Interpretation of Computer Programs, otherwise known as SICP. My name is Conor Hoekstra, and I go by code_report online. Thanks for tuning in on the last day of CppCon 2020. I hope you guys have enjoyed the conference just as much as I have. So all of the slides and the code examples for this talk are posted on my GitHub page. You can follow these links if you'd like to check them out. And there will also be links provided at the end of the talk for other resources. So a little bit about me. I'm a senior library software engineer for NVIDIA. I work on the Rapids AI team, where we focus on building a end-to-end data science pipeline on the GPU. If you want to know more, check us out at rapids.ai, and NVIDIA is always looking for top talent. There are a few open positions on the Rapids team right now, so if you're interested in checking that out, go to careers.nvidia.com and punch in Rapids, and you'll see the open positions. I am a programming language enthusiast. I primarily code in C++, but I love all programming languages and am typically learning a number of languages at any given time. I love algorithms and beautiful code. Be sure to check out my other talks if you haven't seen them already. I'm the organizer of the Programming Languages Virtual Meetup, which I'll say a little bit about in a couple seconds. And I have a YouTube channel, which primarily focused for the first 2 years on solving competitive programming problems in a variety of languages. But more recently, it has been the place where I upload the pre-recordings of the meetup that happens every Monday at 8 p.m. Eastern Standard Time, because obviously that is not a very convenient time for people in different parts of the world. So as I'm trying to be as inclusive as possible, I post these pre-recordings for those that time zone and time doesn't work out, they can watch them online. So this talk is all about the structure and interpretation of computer programs. I'm going to break it up into sort of 3 sections. The first section, we're going to take a look at what people have to say about the structure and interpretation of computer programs. The second is going to be some high-level highlights of things you can expect to learn and see in the book, or at least in the first sort of 3 to 4 chapters of the book. And then in the third section, we are going to look at 4 problems from the book, and we're going to solve them in C++. And then there'll be a short conclusion at the end. Note that this talk is not supposed to be a comprehensive summary. I have had to cut a lot out of this talk. In my first couple practice runs, this talk went way longer than an hour. So a lot of it has been carved out. And this is sort of the SICP talk light that I had originally envisioned. But nonetheless, I still hope it is going to be a great sort of taster, if you will, for what you can expect to see in SICP, as it is an amazing textbook. So, reviews for the structure and interpretation of computer programs. If you saw my lightning talk on Tuesday, you will have already seen this quote from Brian Harvey, who is a professor, or was a professor at the UC Berkeley, where he said, it is the best computer science book in the world. And he taught an introductory course there for over 25 years, 61A, where all of the lectures are now online for free. The next quote we have is from Peter Norvig, who is the author of one of the most well-known textbooks on artificial intelligence. And he said, probably the best introduction to computer science. Moving on to Paul Graham, the founder of Hacker News and the co-founder of Y Combinator, he said, one of the great classics of computer science. Adam Thornhill said, simply the best programming book I've ever read. It changed the way I approach programming. And last but not least, amazing, startling, it has become a kind of Bible for me. And this is from the first episode of one of my favorite podcasts, Functional Geekery. I highly recommend, if you are interested in programming languages or in functional programming, you check this podcast out. And this was actually, at least from what I can recall, the first time I heard of the structure and interpretation of computer programs. The first 15 minutes of this inaugural episode of the podcast is spent on explaining why this book is so fantastic and why everybody should read it. So I highly encourage you go check that podcast out. The second time, at least that I can recall, that I heard about SICP was in November of 2018 at the Silicon Valley Bay Area Python user group. which is hosted at LinkedIn headquarters, there was a presentation being given, and the individual presenting posted 5 great books that they thought everyone should read. And you'll note that second from the right is the structure and interpretation of computer programs. And note that the book right to its right is what is, or at least the presenter at the time said, is the unofficial sequel to SICP, which is CTM, the Concepts, Techniques, and Models of Computer Programming. And that is probably going to be a book that we cover in a follow-up series in the Programming Languages Virtual Meetup. So going back to Brian Harvey, who the first quote was from, he also wrote an article called Why SICP Matters. We're not going to go through the whole article, but we're going to look at highlights from the first paragraph, which I think are pretty powerful. The first paragraph states, SICP was revolutionary in many different ways. SICP is about standing back from the details to learn big picture ways to think about the programming process. It focused attention on the central idea of abstraction, the idea of functions as data, and 3 different programming paradigms: functional, object-oriented, and declarative. And I highly recommend, if at the end of this talk you aren't convinced that you should go and read this book, you go and read this full article at the hyperlink provided at the bottom. It talks so much more than just about it being sort of a textbook in its own class. It talks about why Scheme is such an amazing language. It's the language, the Lisp dialect that they use in the book to teach programming. And it talks about why the programming language usually just gets in the way of the fundamental ideas that most introductory CS courses are trying to teach. And on top of that, as it mentions in this, right on the slide here, it teaches these fundamental ideas in different programming paradigms. And for those of you that aren't familiar, I am sure many of the attendees are, and many of the YouTube watchers at a later date are. But for the first couple of years, as I didn't study computer science in university, I wasn't familiar with the term programming paradigms. And most times when people mention programming paradigms, they don't actually mention what they are. They just mention it sort of in the abstract. If you aren't familiar with the idea of programming paradigms, I highly recommend going and reading Programming Paradigms for Dummies, What Every Programmer Should Know. It's a paper by Peter Van Rooij, who is also the author of the CTM textbook that was mentioned just previously. It's a fantastic read. 1, because it goes through a bunch of different paradigms, but 2, because it doesn't just go through 3 or 5 or 7. It goes through like 40 plus different paradigms. So a lot of people are familiar with functional programming or object-oriented programming, or a couple others, but this is it's a non-exhaustive list, but it's a lot more comprehensive than you might see in a lot of other places. This brings us to the highlights section of our talk. So we're going to start with some quotes, which are primarily taken from the dedication and the forewords to the book. The first quote we're going to start with is probably one of my favorite quotes, and this is how the textbook starts off. It's from Alan J. Perlis, and it reads, "I think that it's extraordinarily important that we in computer science keep fun in computing." For those of you that don't know anything about Alan J. Perlis, he was a former president of the ACM, and most importantly, the first recipient of the Turing Award. And he is a pioneer in the field of computer science, in my opinion. I think this is fantastic. It's a fantastic way to start a textbook. You know, most computer science courses, students don't associate with like having fun. But I absolutely love programming. I absolutely love algorithms. I love beautiful code. And to see someone who is so prolific at the beginning of a textbook starting off with, let's remember to have fun, I just think is awesome. Another quote from Alan J. Perlis: "A programmer should acquire good algorithms and idioms." Now this, if you are from the C++ community, should sound quite familiar to some statements that other individuals in the C++ community have said.
So you have all these algorithms at your disposal, right? Learn them. It's very important.
You need to know the patterns and the idioms that we use.
So, of course, most of you will be familiar with these two individuals. That is Sean Parent from his amazing 2013 C++ seasoning talk, and Kate Gregory from her amazing It's Complicated keynote from Meeting C++ 2017, I believe. So the point that I'm highlighting here is this is a great quote talking about how it's important to know the algorithms and idioms in your language. but also that this has been being talked about for decades now. It's not just Kate and Sean and other people in the C++ community. This book was originally published in 1986. I'm not exactly sure when the foreword was written, but you could imagine that it was sometime in the 80s, which means people have been talking about this for decades now. Yeah, don't listen to me, listen to Sean, listen to Kate, and listen to Alan. The next quote, which is a bit of a mouthful: the discretionary exportable functionality entrusted to the individual Lisp programmer is more than an order of magnitude greater than that to be found within Pascal enterprises. So this I included because it highlights how amazing Alan J. Perlis is with words. You'll see that even more in a second. But it's also highlighting the power that comes with Lisp. There's many different quotes about this sort of phenomenon. But what Alan is trying to point out here is that you are entrusted with so much more power when you are programming in Lisp than you are with other languages, which makes it an amazing tool to learn with. The next quote we have is also about Pascal and Lisp. Pascal is for building pyramids, imposing, breathtaking static structures built by armies pushing heavy blocks into place. Lisp is for building organisms, imposing, breathtaking, dynamic structures built by squads, fitting fluctuating myriads of simpler organisms into place. So once again, you can see here, Alan J. Perlis is just amazing with words and describing the differences between what you're doing when you're programming in Pascal versus what you're doing when you're programming in Lisp, building pyramids versus building organisms. And last but not least, a quote which is not from Alan J. Perlis, but is just from the preface to the first edition. Scheme, the dialect of Lisp that we use, is an attempt to bring together the power of elegance, power and elegance of Lisp and Algol. So at this point, when I had read this, I had no idea. I knew Scheme was a dialect of Lisp, but I didn't know that it was an amalgamation of the ideas in Lisp and the ideas in Algol. And it was at this point that I went and did a little bit of research. And so now we're going to dive into a mini history of Lisp. So this is not meant to be comprehensive at all, just to give you an idea of all the different flavors of Lisp that are out there and sort of how Lisp led to Scheme and how that led to Racket. So this is a diagram stolen from the Lisp Wikipedia page that shows sort of all the most popular Lisp dialects in time. Lisp was originally invented or created in the late 50s by an individual by the name of John McCarthy. And from there, it went on to inspire a ton of other Lisp dialects. I'm not going to read through them all, but any of them that I could find a logo for, I'm going to highlight. So after Lisp came Scheme, then came Common Lisp, then came Emacs Lisp, Pico Lisp, Racket, Guile, which is a Scheme implementation, Clojure, which was invented more recently by Rich Hickey, and Hi, which is, I believe it's a Python-flavored Lisp. So of all these Lisps, at least from my podcast listening and reading and researching, the two most popular seem to be Racket and Clojure. Clojure is definitely the most modern of the two. And so note that even though the book is written with its exercises in Scheme, it's very easy to do the exercises in any Scheme or in any Lisp dialect, let alone any other language. And there's tons of resources online in order to check solutions in different languages. And note that all of the lectures and the book are free. So that is awesome. Talking about the relationship between Lisp, Scheme, and Racket, I had listened to many podcasts and always heard Racket and this variant of Scheme called PLT Scheme sort of used interchangeably, and I never really understood the difference. So this is the relationship between Lisp, Scheme, and Racket. Lisp was created first, then Scheme, then Racket. Lisp, as mentioned before, led to, in combination with Algol, Scheme. So in the late 50s, Lisp was created by McCarthy, and Algol in the early 60s was created by the Algol Committee, which included Alan J. Perlis. He was one of the members. And this led to Scheme, which was invented in the mid-70s, and this was created by Sussman, who's one of the co-authors of SICP, and Guy Steele, who's a prolific author. He's written books on Java, C, Lisp, and more. And then this led to the PLT research group in the 90s, creating something which was originally called PLT Scheme, but at a certain point, this was decided that it was different enough from the original Scheme that they needed a new name. So they rebranded it Racket, but you can see the similarity between the two logos because essentially Racket is just an evolved form of Scheme. So that is your mini Lisp history. The next highlight is a quote that many of you may or may not have heard of, and that it's just data. So one of the first times this really stuck in my head was when I was watching one of the best talks I've ever seen, every Clojure talk ever. And it was given at ClojureCon 2018. And in that talk, it's about 30 or 40 minutes, there is a 2.5 minute advertisement that they made for Clojure. I couldn't find this posted individually by itself anywhere, so I re-uploaded it to my channel. I highly recommend, if you have 2.5 minutes to spare, you go and watch the whole thing, because it is absolutely amazing and hilarious, and probably one of the funniest things I've seen sort of in the programming world. But we're going to take a look at just a short 7-second clip from this advertisement.
It's just data. It's just data.
It's not code, it's data.
No code, only data.
It's just data.
It's better to have 100 functions operate on one data structure than have 10 functions operate on 10 data structures.
So hopefully the audio of that is you can hear. Please let me know in the chat if you cannot. So this is interesting for a number of reasons. One is that it's talking about this phenomenon of it's just data, code is data. The second, though, is that this last quote that we just heard is from Alan J. Perlis. And I actually saw in the chat earlier, someone posted the epigrams on programming. And sure enough, that is what I have a link to at the bottom of my slides here. So, and this exact quote, I'm not sure if it first showed up in the structure and interpretation of computer programs, but it is exactly in there. So here it reads, in Pascal, the plethora of declarable data structures induces a specialization within functions that inhibits and penalizes casual cooperation. It is better to have 100 functions operate on one data structure than to have 10 functions operate on 10 data structures. As a result, the pyramid must stand unchanged for a millennium. The organisms must evolve or perish. So like I said, this is from Alan J. Perlis's Epigrams on Programmings, which is a collection of quotes of his. Another one of them, I believe, is Lisp's. Lisp programmers know the value of everything and the cost of nothing. So there's these very sort of many witticisms that come from him that are quite cool. So I thought it was interesting that there's sort of this circularity that when I was learning about the code as data, I thought about this ad. Then when I went and rewatched it, it had a quote exactly from Alan J. Perlis. So pretty funny. So what is this talking about, though? The first thing we need to look at is a sort of cons in a scheme or any Lisp dialect. So cons is the equivalent of what we have in C++ as a pair, sort of loosely. If you see here, we've got define P cons of 42 and 1729. This is basically defining a pair of the values 42 and 1729. And the two ways to get to the first value and the second value are car and coulter. Note that this is sort of a relic of the old Lisps. The newer Lisps call these two variables or accessor functions differently. If we take a look at a table for what these are called in different languages, you can see Scheme calls these car and coulter. Racket calls these first and rest, as does Clojure. Haskell, Elixir, and OCaml all call these head and tail, although Elixir and OCaml drop the EA and AI, so I guess they don't have the time and energy for vowels. C++ almost has the equivalence of these. We have a ranges views tail in the range v3 library, so that might show up in the C++ ranges at some point. And we don't have head, but we can get the same behavior by doing a take one. And in APL, note that we can get this by doing take one and drop one, which is basically how all of these can be implemented. So if we go back to our code and we compare this to what this might look like in C++, we have the following. So we're creating a pair here. Note that we're using C++ 17 CTAG, class template argument deduction, so we don't need to specify the type. And in order to get access to our first and second values, we can just use the first and second member names. So what is this about? It's just data. Well, in the book for the scheme, they show this implementation of cons, which is basically code for thought. We have a procedure, cons, that takes two parameters, x and y, and then defines an internal procedure called dispatch, which takes a message, and then in this conditional expression, you can just think of this as a case, it checks whether the message is car or coulter. And if it's car, it returns x, and if it's coulter, it returns y. And then once we finish defining this internal procedure, we just return that procedure from our outer procedure cons. And this is really interesting because you'd think of cons as sort of like a data structure or holding data, but here we have defined cons to return another procedure, which is interesting. And this is the whole idea that, or at least this is the beginning of the idea that code is just data and data is just code. And if we look at the equivalent in C++, it might look something like this. Now, I'm not advocating you to write code like this. This is just code for thought. So we have our scoped enumerator with two values, first and second, and then we have our procedure pair that takes two parameters, x and y, and then returns a lambda expression, technically a closure object. And this is going to capture the two values, x and y, and then our lambda that we're returning is going to take a single parameter am our message, and it's going to check if our message is equal to first, then to return x. Otherwise, it's going to return y. I mean, note you could do this a lot more succinctly with a ternary operator. This is just slideware to try and make this point as crystal clear as possible. And like I said, this is just code for thought that we can represent what we typically think as data or data structures. We can implement these all with functions, or what they call procedures in Lisp dialects. And sure enough, if we write the code to sort of get access to these, we define P to be a pair of the values 42 and 1729. And then we can print out by sort of passing the corresponding enumerator value that we want. So either the first message or the second message to either get the first value or the second value. So this is, like I said, it's just the starting point for thinking about code as data and data as code. And this really starts to melt your mind when you get to chapter 4 and you start implementing a metacircular evaluator, which is implementing an interpreter for scheme in scheme. But unfortunately, due to time constraints, we're not going to be able to say much about that in this talk. Next up, we have one of the most important ideas in the first 3 chapters of the book, which is the idea of data abstraction. Here is a snippet from the textbook, which reads, "The general technique of isolating the parts of a program that deal with how data objects are represented from the parts of a program that deal with how data objects are used is a powerful design methodology called data abstraction. We will see how data abstraction makes programs much easier to design, maintain, and modify." This is an extremely important point that they build on and build on and build on. They introduce it at the beginning of chapter 2, and they continue to build on it to the end of chapter 2. This is the idea that you have your sort of user consuming code. So here in the example in the textbook, they have a sort of data object of rational numbers. And at the top level, the users are consuming it here. And then we have our constructors and selectors in C++. Think like constructors and get methods or accessor methods. And then underneath, we have the representation and the implementation. And the point that the textbook makes is that your implementation and representation, the user should not care about this. And if you design your programs well, you should be able to swap out and in different representations and different implementations without your end user caring about it. This is an extremely powerful idea. And it actually was not the first time that I had heard this idea. As this is a C++ conference, I'm sure many of the people watching this are familiar with the Scott Meyers Effective C++ book series. And in the Effective C++ book, his first book, there is an item that specifically talks about this. Item 23, prefer non-member, non-friend functions to member functions. We're not going to go through this whole point. And that's actually, we're not even, the point of the item is not what we're going to highlight. We're going to highlight a specific paragraph from this point that talks about encapsulation, which was incredibly important when I read it for the first time. So from this point, item 23, it reads, "We'll begin with encapsulation. If something is encapsulated, it's hidden from view. The more something is encapsulated, the fewer things can see it. The fewer things can see it, the greater flexibility we have to change it, because our changes directly affect only those things that can see what we change. The greater something is encapsulated, then the greater our ability to change it. That's the reason we value encapsulation in the first place. It affords us the flexibility to change things in a way that affects only a limited number of clients." So in different words, this is basically talking about the same idea, that if we design our classes in C++ correctly, we can sort of change things without affecting our users. We're affecting the minimum number of things possible. So that's all I'm going to say about data abstraction. I also highly recommend all of these books if you have not read them. They are absolutely amazing, and there's no way you can read them and not learn something from them. And last but not least, from our highlight section, we are going to talk about object-oriented programming, ? So we're going to cover this pretty quickly, but at the end of the object-oriented section in the Berkeley lectures taught by Brian Harvey, they have you watch a talk about Smalltalk by Dan Ingalls, who's one of the main implementers of the Smalltalk language, which for those of you that aren't familiar, was the original OOP language. And they have this table, which I thought was absolutely fascinating. So this table states 3 prerequisites you need to have in order to be an object-oriented language. The first is closures, otherwise known as lambdas. The second is everything is an object, aka uniform reference. And the third is garbage collection. Note that these lectures were given in 2010. So at the time they had no planned, meaning that they were coming in C++11, and in Java they said kind of, because you had, I believe, like the single accessor methods. I'm not a Java expert, but there was a way of sort of simulating a closure type object. But now in 2020, we both have closures in C++ and Java. So this is what the table up to date now looks like. But the point that Dan Ingalls and the Smalltalk folks were stating was that you don't have an object-oriented language unless if you meet all 3 of these criteria. So apparently C++ is not an object-oriented language, according to Alan Kay and Dan Ingalls. Obviously, I'm sure there are many people that disagree with this. It's odd that you would think that GC is a prerequisite for an OO language. But yes, this is just what the creators of Smalltalk, like I said, which is the original OOP language, that's what they have to say about what makes a language object-oriented. And with that, I believe we have come to my favorite half of the talk and section of the talk, and that is solving problems in C++. So I had to cut out a bunch of these because there's so many amazing ones, and depending on our time, we may even need to skip one of these, but it looks like we're doing all right. We're going to look at 4 problems. The first one's a warm-up, and then the last 3 are problems that are taken from different chapters in the book, and we are going to solve these in C++. And I think this is going to be a lot of fun. So let's start with our warm-up problem, similar to a problem that I originally covered in my very first talk, Algorithm Intuition, that I originally gave at C++ Now. So the warm-up problem is entitled Sum Square of 2 Largest, and it states the following. Given a list of n, where n is greater than 1, positive integers, return the sum of the squares of the 2 largest numbers. So you can feel free to post what you think your solutions might be in the chat. I know there's a little bit of a lag. But for example, if our list of numbers is 1, 2, and 3, the solution would be 2 squared plus 3 squared, which is 4 plus 9, which is 13, because 2 and 3 are the 2 largest numbers. And for a final example, if we have the numbers 1, 8, 2, 6, and 3, the 2 largest are 8 and 6. 8 squared is 64, 6 squared is 36. Add those together and you get 100. So hopefully the idea is pretty clear. And while you're thinking about it, I should note that up until this point and from this point, all of my examples were coded in Compiler Explorer. Thank you, Matt. It's an amazing tool, and all the people that work on Compiler Explorer. The flags I used and the compiler I used was GCC 10.2 with C++20 and O2. All of the Gobalt links, as I mentioned at the beginning of the talk, are posted on the GitHub page with the code examples. So let's take a look at the first solution. So we're not going to cover the suboptimal solutions. I do have some suboptimal solutions posted on my GitHub, but in the point of trying to not take too long to go through this solution, we're just going to look at what I consider to be sort of the 3 most elegant. So the first is using std accumulate. So what we're doing here is we are using std accumulate to initially create a pair of values, 0 and 0, which are going to represent our 2 largest values. And then for each value in our range, which we're getting access to with our cbegin and cend, we are going to iterate, use C++17 structure bindings to destructure our pair. So A is the largest value, B is the second largest value. And then for each element, we do the following check. If E is greater than our largest value, so the current element we're looking at is greater than our largest value, then we store our current largest in B, and then reset our largest to be equal to the current element. Otherwise, if we know we're not bigger than the largest element, if we're bigger than the second largest element, reset B to be the current element, Otherwise, we know that the current element is less than both our two largest that we currently have, so just return the pair. And then at the end, we square both of them and add them up. So this is quite a nice solution, in my opinion. However, we are going to go on a small digression. So this, I'm actually going to check to see in the chat if anybody knows. Does anybody know who this quote is from? We write awful code. And while you're typing, I'll add a second piece of it to see if this gives you any more hints. We write awful code. I think that the starting point for all of us is to just admit to yourself that you write awful code. I do see that Victor has the correct answer. And so let's take a look at this actual quote.
It's not a unique. Google is not specifically, I mean, it is an awful place. But it's
I could have picked on Adobe as well, though.
It's, you know, they have awful code at Adobe. They have awful code. We write awful code. And I think that the starting point for all of us is to just admit to yourself that you write awful code.
So congratulations, Victor. You were indeed correct. This is from Alexander Stepanov, the author of STL, from the extended version of C++ seasoning. So if you are a huge fan of C++ seasoning, there's links at the end and links on GitHub to a 2-part extended version of this talk, which is hosted on the A9 Videos YouTube channel. A9 is a subsidiary of Amazon that works on search. And I think this is extremely important. As presenters, and I think as C++ developers in general, at least I know I am terrified of making mistakes and like showing that I write bad code. And when I saw this from Alexander Stepanov, it was like it's amazing. It's seeing one of the foremost experts in template meta programming and algorithms talking about how we all write awful code. I know the word awful is a bit negative, but think about it as just like we all make mistakes. And he goes on in this conversation with Sean to talk about how it's important to discuss your code the same way that mathematicians discuss proofs with each other to get to like the ultimate version of your code. And so at times now, when I make mistakes, I'm going to leave them in my slides and then correct them later and say, just as Stepanov said, we all write awful code, we all make mistakes. And I think it's important, especially as sort of leaders in the C++ community, for all the other C++ developers out there to see that even the people at the top, we're all writing bad code and we all need to help each other to write better code. So this is really important. While we're on this digression on Stepanov, on stepanovpapers.com, which is a website that everybody should familiarize themselves with, we can scroll down to the source code section. And this was, when I discovered this for other reasons, but this was just so amazing. The first bullet point in this section is a Scheme Higher Order Programming Library in 1986. I'm not sure if that's a coincidence that it came out in the year that the structure interpretation of computer programs came out. But you can see here on this page that the standard template library was implemented in multiple languages before it was implemented in C++. You can see here there's the Java algorithm library, there's the Ada generic library, the Scheme Higher Order Programming Library. This is very faintly sort of resembles what STL ultimately became. But if you need another reason to go and read CppC, know that the father and the author of the standard template library, when he was first exploring the ideas of generics and higher order programming, explored it in Scheme. And here's just a small snippet from the 81-page paper. This paper is amazing. I haven't fully read it, but it's amazing for multiple reasons. One, you can see sort of here's the reduction operator that is making use of iterators. He's exploring the idea of iterators here. But on top of this, the paper is scattered with little history tidbits. So you can see here, he's mentioning that the reduction operator was introduced by Kenneth Iverson in my favorite programming language, APL. And he has multiple of these sort of like little shout outs to other programming languages and sort of historical tidbits, which is just amazing. So another reason to read CppC and to learn Scheme. Alexander Stepanov was doing this, ages ago. What is that? 34 years, 35 years, depending on when you're watching this on YouTube, maybe even later. End of digression. So why did I go on that digression? Well, I'm sure that there's some of you looking in the chat or looking at the screen and thinking in your head, why are we doing a std swap here? I realized this a couple days ago, and it was devastating because this was a question that I had asked for months a couple years ago in interviews. And so I'm very familiar with the answer to this question. Yet when I coded it up in preparing for this talk, for some reason I used a std swap. And if you're familiar with Andrei Alexandrescu's talk, There's Treasure Everywhere, you'll know that you should try to avoid swap whenever possible. This talk delves into a couple different algorithms and optimizing them. And in one of them, he looks at, I believe it was std partition, and uses this idea of something called vacancies. If you're interested, go watch the talk. It's amazing. But how using a vacancy, which enables you to avoid a swap, can lead to, like, in some cases, performance increase of like 40%. And so using this swap here is super, super suboptimal. It doesn't make a performance difference in this code, but it's unnecessary. And it also makes the code a little bit harder to read, in my opinion. So we can replace this with just setting B to be equal to A, because that's essentially what we're doing. We don't need the other side of the swap, and we don't need the temporary copy that comes with that swap. So in the first case, if our current element is greater than A, just set B. So you're basically shifting their top value A down to B, and then setting A equal to E. So that's all I have to say about this solution. You can see here we're using C++20 concepts in the most general way that we possibly can by using the auto keyword. We're also making use of C++14 generic lambdas. We're making use of C++14 function deduced return type. We're making use of C++17 structure bindings. And last but not least, we're making use of C++17's CTAD class template argument deduction, and the fact that we don't have to specify the explicit return, the explicit types of pair. So this code makes me really happy. Some would argue that it's not as nice as a for loop, and I would have to vehemently disagree. We can use const at the top here because we're using an algorithm, and for me, this is elegant code and the way that I would like to solve this problem. Let's take a look at a couple other solutions which are not as efficient. So a couple of you might have been thinking of a certain algorithm, and that is nth element. So here is a very verbose solution that is basically taking the top two elements from our range and putting it at the front. And then we have transform to square the values and then accumulate to reduce them. This is a bit verbose, in my opinion, for just squaring and summing up two values. So I personally prefer this version, but I'm sure there's differing opinions on which is better. And note that we are making use of the C++20 range algorithm nth element. So instead of having to pass 3 iterators here, we're passing the data structure V and then only 1 iterator. So this is really nice. I love the range algorithms that are coming in C++20. Note that one of the downsides of this, though, is that we have to modify the original data structure. So in that case, in that sense, it's not optimal, and also too, nth element isn't going to be anywhere nearly as performant as just a single reduction. So if we take a look at what modern features we're using here, C++20 concepts again, C++14 function deduced return type, CTAD once again from 17, and C++20 ranges. And just for curiosity's sake, I profiled these two. So this is with 5 elements. Std accumulate versus the 2 different nth element solutions. So clearly accumulates better. And when we kick up the number of elements, of course, accumulate continues to do better. And also on the GitHub, not in the slide deck, I have profiling of comparison against accumulate versus for loops. And sure enough, the profiling shows that accumulate is in all cases just as fast or faster than raw for loops, which is fantastic. So that is the end of our problem 1. I can see, or warm-up problem, I should say. I can see we have a question, which is just a troll from JF, so we're not going to read that. Moving on to problem 1. So this is called even Fibonacci. And this problem looks at basically 2 different problems. So you can see here we have even Fibonacci versus some odd squares. So in the book, it shows 2 different procedures, one called sum odd squares, and then one called even fibs. I'll quickly go through this, but it's not super important to understand what this Lisp code is doing. But essentially, given a procedure that takes a single argument that takes a tree, we want to basically collect all the odd values at the leaves of the tree and then sum them up. So we're using a conditional expression. Once again, you can consider this to be like a C++ switch case statement. And then we've got our base case where our nodes are empty. We just return 0. Then if we are at a leaf node, then we want to check, is it odd? If so, square it. So I guess, yeah, sum odd squares. I missed out squares in the implementation. Otherwise, return 0. And if we're not at a leaf node, then we're just going to go to our else condition and recurse down by calling sum odd squares on the car and the cdr of the current node that we're at to go down the left branch and the right branch. If we move to our next solution, we're going to go through this one even less, and this is basically generating even Fibonacci numbers. So we're doing this with an internal procedure. So even fibs takes a single integer n, and then it defines a internal procedure called next. And then inside here, basically, you can see that there's an even in an if expression happening. And ultimately, what this code is doing is it's making use of this fib function here to generate Fibonacci numbers in linear time. So this is a very suboptimal solution, and it's filtering out any odd Fibonacci's and just keeping the even ones. And we kick off this outer procedure even fibs by making a call to the internal procedure next. So like I said, it's not entirely important to understand what this code is doing. The point that I want to highlight here is that the textbook goes on to show the following. So if we switch back to our even fibs, or look at our even fibs with the fib code, the textbook points out the following, is that these two solutions don't look like they have much in common. But if we actually implement them in terms of algorithms or higher order procedures, we can see that we can make use of a lot of the same algorithms, those being accumulate, filter, and map. So at the bottom here, we have a different implementation of even fibs that makes use of accumulate, makes use of filter, where we're filtering in the even ones, and then makes use of map. And then enumerate interval here is similar to iota and C++. We could reorganize this code at the top here so that we have the outer procedure now as an internal procedure. But the point here is that we're making use of these algorithms, which makes the code a lot easier to read, is one of the points that this textbook points out. And there's an amazing footnote, which I'm going to read, and it's by far my favorite footnote of the book. And there are an amazing number of footnotes in this book. So the footnote reads, Richard Waters in 1979 developed a program that automatically analyzes traditional Fortran programs, viewing them in terms of maps, filters, and accumulations. He found that fully 90% of the code in the Fortran scientific subroutine package fits neatly into this paradigm. And if we go to this paper, the paper is called A Method for Analyzing Loop Programs in 1979. So, you know, Sean Parent, he's been talking about loops more recently, but even back in the 70s, they were analyzing loops and saying the following. If we go to the part that mentions the 70%, it says of the 273 augmentations, 243, 89% were easy to recognize as either a product, a sum, a max, a min, a count, or a trivial augmentation. So a trivial augmentation referring to the maps and the filters. So this is unbelievable. 1979, and they're doing analysis of code in Fortran and finding that 90% of the for loops could just be algorithms. So just absolutely phenomenal. If we go back to the footnote and continue to read, it says, one of the reasons for the success of Lisp as a programming language is that Lisps provide a standard medium for expressing order collections so that they can be manipulated using higher order procedures or operations. The programming language APL owes much of its power and appeal to a similar choice. In APL, all data are represented as arrays, and there is a universal and convenient set of generic operators for all sorts of array operations. So just for fun, to look at what each of those 5 reductions that were mentioned in the paper, this is product, multiply, reduce. This is sum, plus reduce. This is max, max reduce. And this is min element, min reduce. And this is count. So this textbook mentions APL, and every single one of the 3 professors, Sussman, Abelson, and Harvey, across the MIT and Berkeley lectures at some point talk about APL, which is just fantastic because I think there's a lot we can learn from APL. So if we take a look at the C++ version of the even fibs code that we saw before, this is what it might look like. We are using RV as a shortcut namespace for stood ranges views. We can first zoom in on this fib function, which is our helper function to, in linear time, calculate Fibonacci numbers. I'm not going to spend much time on this, but it's sort of cool because we have a recursive lambda here, essentially. By default, if you're just using the auto keyword, you can't have a recursive lambda. But if you use a stood function to explicitly declare the type of your lambda, you can then capture it and call it, which is super awesome. And so you can see the same way that we were kicking off our fib function by making a call to the internal procedure next, we are making a call to the internal quote unquote lambda fib iter and passing it the values 1, 0, and n to kick off this fib function. If we zoom out and then zoom back in, this is probably one of my favorite pieces of code from this presentation, because this is completely possible in C++20. So this is making use of the ranges views in the ranges header, which is available on Godbolt and GCC 10.2. You can see here that we're creating a list of the numbers 0 to n plus 1 exclusive, so basically 0 to n, then transforming them using the Fibonacci helper function that we just implemented, and then filtering out any of the odd numbers, aka filtering in the even numbers. And this will do the exact same thing that the previous code that we saw in Scheme does. This is just, it's so elegant in my opinion. This is just beautiful. I absolutely love piping operations together like this. And when you compare this to sort of the non-idiomatic, non-ranges code that just uses for loops, it's not even a close contest in my opinion. So if we zoom out once again and look at all the features, we've got C++20 ranges, and all of these, iota, transform, and filter, are in C++20. We've got C++20 concepts using auto, which isn't constrained, but we could constrain it if we wanted to be more comprehensive. C++14 generic lambdas, and C++14 function deduce return type. So awesome. Gotta love modern C++. Moving on to the second last problem, which we're going to go quickly through because I've only got 13 minutes left. And this is focusing on some approximations of pi. So in the book, there are, this isn't even an exhaustive list. There's Monte Carlo estimations for pi, as well as I believe a couple others. The first estimation for pi here at the top is attributed to John Wallace. We're not going to look at this one, although in my opinion, it's the most interesting. And I promise I will come back to this in a future talk. But the two we're going to focus on are the Leibniz approximations for pi. So these are just two statements of the same approximation. And we're going to look at how to solve these in C++ using ranges once again. So we'll start with the one at the bottom. So we've got pi over 8 is equal to 1 over 1 times 3 plus 1 over 5 times 7 plus 1 over 9 times 11. So how could we go about solving this? The first thing, a good starting point, would be to generate odd numbers, because then we have sort of the values that are needed for the denominators of these fractions. Once we have the odd numbers, if we could group them into chunks of 2, that'd be a good next step. Then if we transform each of those chunks by multiplying them together, because that's what the formula does, multiplies them, and inverting them, we then have the different fractions needed to compute this value. And once we're done this, all we have to do is add them up and multiply by 8, and we're done. And so I've sort of cheated here a little bit by explicitly using the words that I need for the algorithms. But we've got generate, chunk, transform, and add. So a common generate function that we've already seen a couple times is iota. And then we can pipe the results of iota 0 to n to transform to get our odd numbers. So iota plus transform is a neat way of getting odd numbers if you multiply each of those by 2 and then add 1 to it. Alternatively, there's a couple different ways you can do it with different values, but this is just one of them. Once we have our odd numbers here, we just chunk them using a view in range v3 that doesn't exist in C++20, but might exist in C++23, called chunk. And then we transform it once again by multiplying the two values in each of our chunks, which we can get access to using the bracket operators, and then dividing it or doing 1 over to get the inverse. And then we just accumulate using plus and an initial value of 0. This is just in the HS namespace so that we can make accumulate pipeable. Check out Tristan Brindle's ranges talk that he gave yesterday to hear more about sort of the numeric pipeability and implementation of the numeric algorithms that don't exist yet in C++20. And then once we have this, we just multiply by 8. And once again, this code makes me extremely happy. It's the pipeline model. The output of one operation is the input of the next operation. This makes me extremely happy. And if we use format to print this out, you'll get 3.14149, which is pretty close to a couple decimal places. Two approximations are going -1.7. So how to solve this one? A first good step once again would be to generate odd numbers. Then what we need to do this would be to zip with it repeating numbers 1 and -1. So then you end up with tuples of sort of each of the odd numbers and a 1 or a -1. And if we multiply those, so we transform the odd numbers by inverting them to get the fraction, and then by multiplying the corresponding 1 or -1 that they're with, we'll end up with the correct term in our fraction. And then once again, we add these up. We can multiply 4. So taking a look at this code, doing the same sort of trick where we highlight the different algorithms that we need. Note that repeating is in purple because it's on the same line, but also the algorithm that we want for this is an algorithm called cycle. So this is the second approximation for pi using a sort of different formula. Here we have our signs, 1 and -1. Comments in the chat that say, anyone else losing chunks of video? I will continue, and hopefully this isn't a problem for... Oh, I'm back. The video is very choppy. Okay, I slowed down, and apparently it's better now. Hopefully it stays this way. So we have our signs, 1 and -1, that we're going to pass to cycle here. And then we have a call to zip with. So zip with takes a binary operator, or I should say an n-ary operator, and then n ranges. So here we're taking 2 ranges and a binary operator. So we're getting our odd numbers the same way we did in our previous solution, which is piping iota to transform and then doing the 2 times plus 1. And then we're getting a repeating 1, -1 by just passing this to cycle. So once we have these 2 ranges, these get zipped together and transformed with our zip with and our binary operator, which inverts the odd number e and then multiplies it with the sign. And then once we've done this, we just add up all our numbers, multiply by 4, and we're done. And because we are down to 8 minutes, I'm just going to move along. This is a alternate way of solving the problem. Note, once again, Stepanov, we write bad code in that we're using a mutable lambda with a captured sign that just toggles. But this expression here, we do not need to do in order to toggle. We can just multiply by -1 in order to get toggling 1s and -1s. So once again, we write bad code, and we can all do better by iterating and discussing. But yeah, this is the second solution. And as I mentioned, I will come back to the John Wallace pi approximation in a follow-up talk in the future. So last but not least, we have my favorite problem of the whole talk, and it is Ramanujan numbers. So I saw in the chat earlier someone pointing out that, that's awesome that you're using a Ramanujan number in your example. So what is a Ramanujan number? It comes from this footnote in the book that says the following. To quote from G.H. Hardy's obituary of Ramanujan, it was Mr. Littlewood, I believe, who remarked that every positive integer was one of his friends. I remember once going to see him when he was lying ill at Putney. I had ridden in taxi cab number 1729 and remarked that the number seemed to me a rather dull one, and that I hoped it was not an unfavorable omen. No, he replied, it is a very interesting number. It is the smallest number expressible as the sum of 2 cubes in 2 different ways. This is awesome, because when I read this, I was like, wait a second, I've seen this in a movie. There's a movie called The Man Who Knew Infinity, which is the story of Ramanujan. So let's take a look at the clip from this video, and hopefully it comes through okay.
Sorry I'm late. Bloody cab driver got lost. Should have known from his number.
And what was that?
Rather a dull one. 1729.
No, Hardy. It is a very interesting number. It is the smallest number expressible as the sum of 2 cubes in 2 different ways.
So this is awesome. Go check this movie out. I mean, it's not it's not the most amazing movie in the world, but if you're a fan of math, I'm sure you will enjoy it. So these numbers are known because of this, also not just as Ramanujan numbers, but as taxicab numbers. So a little piece of trivia. And depending on the talks that you watched earlier this week, you might have noticed some of these numbers. Was anyone in Stefan Lauerwade's talk? If you look close enough, you'll see 1729. And you'll also see on another slide 1729 down here. So now you know whenever you see 1729, it's because it's a Ramanujan number, and clearly Stefan is a Ramanujan fan. So to recap, the way a Ramanujan number is calculated is you have to have two different ways of expressing the number using the following form. So a cubed plus b cubed for the number 1729. As I see someone just typed in the chat, we have 1 cubed plus 12 cubed and 9 cubed plus 10 cubed. So how can we solve this in C++? And this is what we're going to spend the remaining 4 minutes looking at. So here, there's a lot of code on slide. Let's walk through it one by one. So at the top, we have a lambda that takes a tuple, destructures the tuple on the first line, and then just cubes each of the values and adds them together. So this is just some cubes. It's pretty straightforward. We can hide this away in a little ellipsis to make the code a little bit more clear. Then we have a bunch of ranges. So the first thing we do is a Cartesian product of iota 1 to 33 twice. So what is a Cartesian product? Well, in several different languages, they have it by a different name. So Rust, D, Racket, and C++ all call this Cartesian product. In C++, it exists in range v3. And Python and Ruby, it's called product. And in Q, which is a descendant of APL, it's called cross. There are two other sort of sibling algorithms, inner product and outer product, which I'm not going to talk about here, but it's just good to know. And this is a visualization actually of outer product, but you can think of Cartesian product as just the flattened version of this. So it's given a list of given two lists, it creates combinations of each of them. So that's what Cartesian product does. And if we look at the next line, filter, we're basically filtering out any of the pairs where or filtering in any of the pairs where the first one is less than the second one, and all of the other ones are filtered out. So if we go back to this diagram, this filter is basically essentially doing this. It's only keeping the pairs where the first element is less than the second. And if we go back to this, once we have this, we then transform using the same lambda that we defined up above to get our sort of potential Ramanujan values. We then have to convert this into a vector, and then in order to sort it, and because we're using an action here, we then need to store this in an L value. Once it's in an L value, we can go back to using views where we go adjacent filter to filter out any of them that are not equal to each other when they're adjacent. So that's how we can sort of identify the Ramanujan numbers, looking at the ones that are adjacent and equal to each other. And then we have to drop one because of the way adjacent filter works. I'm not going to talk about that now because I'm very short on time. So the first change, like this is an okay solution, but we're going to iterate to sort of the ideal solution. And so what I really want is a combination of Cartesian product and filter with this exact pattern. So if we had an algorithm called triangle product, we could avoid this filter. And this is a very common pattern that I've seen in sort of array-oriented languages, and I'm surprised this as algorithm doesn't exist. At some point, I will add this to the Range v3 library or write a paper and have someone else do it for me. Once we do this, the next thing we want to do is get rid of this action sort. And this sort of comes from the idea in chapter 3 of SICP of streams. So if we had a modified version of our triangle product algorithm that took an order, we could eliminate this sort and we could eliminate this ranges2 vector. So if we had an algorithm called ordered triangle product that took a weighting, and between the two sort of lists of numbers that were being generated, it would just look at the weighting and take the next one, we could avoid the sort, which would be absolutely amazing. And now because we are no longer using an action, we don't actually need to explicitly provide the number 33, which gets us the first 5 Ramanujan numbers. We can replace the 33 with just a take 5 at the bottom. And then once we've done this, if we combine it with the future C++23 pipeline operator using the placeholder here, we get even more elegant code because we don't need to define iota so we can pass it twice. We can just use the placeholder twice, depending on how it gets designed. And then we have this extremely elegant code, in my opinion. So very quickly, because I'm out of time, if we bring back this code and then highlight all the different features, we have C++20/23/XX ranges. All the ones highlighted in green are available in C++20 now. We've got the C++23 pipeline operator, C++14 generic lambdas, C++17 structure bindings, and yeah, that brings us to our conclusion. So SICP is an absolutely brilliant and timeless textbook. You will learn about the fundamentals of computer science in not just one, but 3 different programming paradigms. Many of the examples and exercises in the text are challenging, but is incredibly rewarding and fun to solve them in whichever language you choose. And it is entirely free. So as well as the MIT and Berkeley lectures, the textbook is free. And I want to say thank you to all of the passionate teachers and presenters that inspire me and other individuals. So obviously Sussman and Abelson, if you watch the lectures, they're absolutely phenomenal. I mean, Sussman actually dresses up as a wizard in one of the lectures. It's amazing. Everyone should watch it. To Stepanov and Sean Parent, you both have been inspiring me since I started watching talks, and I want to say thank you to all the speakers at this CppCon and past CppCons and all the conferences. It's absolutely awesome. And so just a couple last notes. As I mentioned, all the code and links to the talks that I mentioned are on my GitHub. If you want to check out all of the links to the free lectures and the free textbooks, check out the Meetup GitHub SICP page. You can find all of the links here, and all of the videos are linked here as well. And finally, thank you. I guess we're sort of out of time, so I'm not sure how questions work at this point if I get kicked off. I will say before I answer any questions, I will be going to, we'll say, hallway track floor 9 for anyone that wants to chat afterwards about this or has questions that don't get answered in the Q&A period. The first 2 questions are for JF, so I'm just going to ignore them. And then Victor says, Stepanov was a strong proponent of algorithms on arrays, coming really strong against node-based data structures and Lisp-like or Smalltalk languages. I'm not going to click on the link, but I assume that this is, I think I've seen the link that you're talking about where he explicitly mentions that like map and unordered map and set, they come from Smalltalk, and that the reduction algorithms come from APL. I love algorithms that operate on arrays. I think it's a very natural way to think about sort of the pipeline model. If you've worked in any array-oriented languages, you'll find it extremely natural coming to sort of other languages that have reduction operations on arrays or other sequences. So I'm a huge fan. With the opinion sort of against node-based data structures, I don't really have any thoughts. Maybe find me after the talk and we can chat. There's a question from Augustine that says, what other resources for learning that were not mentioned would you like to share? What do I think the best resources are? So there was a lightning talk, actually. I'm not going to remember the name of it, but it mentioned basically like a ton of great C++ resources. So for C++, like the 2 C++ podcasts, CppCast and CPP Chat, all of the free videos online, all of the textbooks. The Scott Myers books are absolutely fantastic. I think they're a must read. It's hard for me to pinpoint like what are the best resources because I just have so many that I constantly consume. I sort of approach it from like the fire hose method. But yeah, maybe sync with me after. And if you've got like specifics on like if top videos or top books or top podcasts, I can point you in the direction of some. Maybe the next question I think is from Romario. It says, I've always felt the elegance of Lisp doesn't fully map cleanly to typed languages. Do you agree? The elegance of Lisp doesn't map cleanly. I I'm not informed enough. I'm not enough of a Lisp expert to answer this well. I know that in Racket they have the typed Racket project, and in Clojure they are also working on like a typed version or spec. But I know that it's a struggle to add typing to like Lisp dialects. And I know Rich Hickey, if you watch any of his talks, he says that static typing does help, but that like a dynamically typed language also has like a ton of benefits, which I do agree with. So yeah, you would have to probably ask a Lisp expert to get a better answer. Next question from Pablo. In the fib with std function, why use std function, i.e. why polymorphic? Is there an alternative, like a better alternative? I was reading online like how to do a recursive lambda, and that was the recommendation that I came across. But if there's a better way, feel free to let me know. And then last but not least is Stepanov was definitely against OOP and thus probably Smalltalk. Not sure about node-based data structures. Okay, so that's just a comment. All right, so it looks like the question queue is empty. Like I said, I'll be on floor 9 of the hallway track if people want to chat about this. Thank you everyone to tuning in, and I hope you enjoy the rest of the conference.